Okay, so this video for tonight is over basic differentiation rules. We kind of learned a shortcut. We learned the power rule today in class, so this is kind of just the extension on that. The target for today is students will find the derivative function more efficiently by applying the power rule and other basic differentiation rules in order to calculate the instantaneous rate of change at any given value. Remember, the purpose for us finding the derivative is to find our instantaneous rate of change, that rate of change of our tangent line. Okay, so here are the formal rules, the constant rule. Just really quickly before we get started, when I write this notation, that means to find the derivative. Okay. It's the operation, kind of like the limit was a plus, a minus. It's just our operation to find the derivative. So that's kind of what that means. So the constant rule. The constant rule says if we take the derivative with respect to x, to our independent variable, of any constant value, so like 4, 5, pi, that will always come out to be equal to 0. The basic power rule says if we take the derivative with respect to x of some variable, our x, our independent variable, raised to some power, that will get that power times our x to the n minus 1 power. Constant multiple rule. Remember, all these rules are the independent rules, but a lot of times we're doing them just naturally within our process. So the constant multiple rule says if I take the derivative, of course, with respect to x of some constant times my x variable raised to the n power, now all I'm going to get is that exponent times my constant x to the n minus 1. And then the sum and difference rule, just like with our limit rule, if we take the derivative with respect to x of some function plus or minus some other function, that will get the derivative of the first function. I'm going to use f prime. Remember, that's our notation for a derivative. Plus or minus whatever it was, the derivative of the second. So when we do our derivatives, so for example, let me put a function here. So that's f of x equals, let's say, x squared plus 3x plus 4. When we take a derivative of something like that, of course, we'll get f prime equal to 2x. What I did right there was, in fact, okay, I can put a 1 power here if I wanted to, was in fact my power rule. That 3x to the 0 power, that's my constant multiple rule because I'm taking that 1, multiplying it by the 3 and subtracting 1. And then, of course, plus 0, and that's my constant rule. And then when I put all of this together, that's my sum and difference rule. So it's kind of natural that we're doing all these rules, but just independently, that's the actual rules and what they're named. Okay, so let's look at some problems. We just discussed in class that in order to use the power rule or any of the rules on that first page, it has to be in power form. Remember, that means some number. I'll put it down here real quick. X variable to some power, that's a number, in the numerator. Okay, so the rules that we've discovered will only apply if in fact they fall into that form. So if my equation is not in that form, I can simplify it, I can rewrite it, I can do a whole bunch of things to get it in that form. So the goal is going to be to get it in that form right there. I'm going to go ahead and erase that really quickly. So for example, our very first example, negative 2 over x squared, that's not in the proper form because my x is not in my numerator. So the first thing that I would want to do is to rewrite it. Okay. That negative 2 stays where it's at. My x is going to come up to my numerator. And remember, changing the sign of our power changes its location. So I can put negative 2x to the negative 2, and that's going to bring it up into my numerator. And then the second part, I don't need to do anything. Okay. Do not differentiate anything until you are ready to differentiate everything. That's going to be a huge problem in here. Do not differentiate anything until you're ready to differentiate everything. I'm going to say it one more and you should know what that means. Do not take the derivative of anything until you're ready to differentiate everything. So there's a lot of times where we'll rewrite a function because part of it is a problem like this one, but that means I'm not going to take my derivative until I'm ready to do everything. So now that everything's in the proper form, now I'm ready for my derivative. Okay. So power rule says to take that -2 and multiply it by the coefficient of -2, which is 4x, and subtract 1. -2 minus 1 will give me -3. Minus 3 times 4 will give me 12x squared. Now, I want to always simplify my equation, meaning I never want to leave my answer with any negative exponents or any rational exponents, so fractional exponents. So I'm always going to want to rewrite after I've differentiated to simplify it out a little bit. So that x to the -3 right here, I need to move it to make that -3 a +3. So for numbers never move, only variables move. X to the 3rd power. Now it's positive because I've changed its location. And I don't need to do anything to that one, so I'm just going to bring it down. And there's my derivative. I'm done. Okay, second example. Now, there's a couple of things I could do to simplify it. We haven't learned how to take the derivative of a quotient, but I can definitely rewrite this to get it into power form. A good habit to have for problems like these, if you have a single variable or a single term in your denominator, one of the good strategies to do is to split up your fraction. Add and subtract, sorry, that is not an x. When we add and subtract fractions, we know we can do that because of the fact that our denominators are the same. So that's really what I'm doing. Okay. So a good habit to have is when you have a single term in your denominator and multiple terms in your numerator is to kind of split them up. And that can help you simplify, because that's what I'm going to do right now. So that becomes 3x to the 3rd minus 3x minus 2. And now that I've simplified that equation, now I'm ready to take the derivative. Remember, I'm not taking the derivative of anything until I'm ready to take the derivative of everything. So now I'm going to use that constant multiple rule. So 3 times 3 gives us 9x, and I subtract 1, which means I get 2, a power of 1. So that becomes minus 3x to the 0 power, if we want to think of it like that. And then that -2 is going to go to 0 because remember, even though it doesn't have an x, it's really x to the 0 power. So it's going to 0 out. So I'm just going to rewrite this because I don't like the way that 0 power is dealing with it. So I'm just going to put a -3. And there's our derivative. Remember, this is the equation that represents the slope for that's specific to the function above. The next example we have a product. We haven't learned a product rule. In our previous page, there was nothing that told us what we could do with products or quotients. So because I don't have a product rule, I need to simplify this. This is a simple distribution, so that's exactly what I'm going to do. So x times x gives us x squared plus 2x plus 3x plus 6. I want to combine my like terms really quickly. And I get x squared plus 5x plus 6. So a lot of this is algebra. We're doing some algebra up front. We're doing some algebra in the end to simplify. That's going to be a big part of this class. Now that I've done that and everything is in that power form that I mentioned before, now I can take the derivative. So f prime. So I get 2x here plus 5. That x is going to go to the 0 power. It's not necessary. And then that 6, remember that 6 has an x to the 0 power, which is the reason why it zeroes out. Okay, next example. Just like the one above, what I'm going to do is I'm going to separate. So x cubed over x to the 5th minus 5x squared over x to the 5th. Okay. Subtracting them out, simplifying. Remember, anytime we're dealing with a rational equation, to simplify it, our fractions, we subtract our exponents. So we wind up getting an x. 3 minus 5 gives us a negative 2. And that's going to be okay for right now. And then, of course, minus 5. 2 minus 5 gives us x to the negative 3. That's in that power form that I want. So that's exactly the form I need it in so that I can use my power rule and my constant multiple rule from above, or from the previous page. So here's my derivative. So, of course, negative 2 comes in front, x, and we subtract 1, gets us negative 3. Minus that negative 3 times that negative 5 is going to give us a positive 15. And then x to the negative 4 when I subtract 1. Again, I never want to leave negative exponents in my answer. So I'm going to fix that situation. So that negative 2, numbers never move, so it's in the numerator, leave it in the numerator. But the x coming down can make that a positive 3 plus 15 over x to the 4th. Now you can leave your answers like that. There's no need to simplify it to get it down to be one fraction. If you would like to do that, of course, it's just finding a common denominator. This one's not too hard or too difficult to do that with, but really this is as far as you would have to go in the simplifying process. Okay. Let's look at another example. It says, at what values of x will the function have an instantaneous rate of change of negative 2? We want to know when our instantaneous rate of change, f prime of x, is equal to negative 2. So if I want to know when f prime of x is equal to negative 2, the first thing I need to do is to actually find f prime of x. So that's exactly what I'm going to do using my power rule and my constant multiple rule. When I get that, I want to know when 3x squared minus 2 is equal to negative 2. So of course, after that, it's just a matter of solving. So add 2 to both sides. I get 3x squared is equal to 0. So that means x squared, not x cubed. X squared is equal to 0, which means x must be equal to 0. So the only time my instantaneous rate of change or my slope of my tangent line is going to be negative 2 is in fact when x is equal to 0. Okay, so when it comes to our trig functions, they have their own special rules. Remember, trig has its rules just like anything else. So even in the derivative process, integral process, anything we do in here is also going to have its rules. So what I will let you know is if I want the derivative of sine f prime of x, I'm going to actually get positive cosine of x. And we'll leave it for right now. On cosine of x, if I get f prime of x, I actually get negative sine of x. Now, with these two, I'm not going to go out throughout the whole process in this video because it takes some time. What we'll do in class is we'll go over one. I'll prove to you that these derivatives are in fact those derivatives. But these are those that you just want to kind of know, that you need to kind of have memorized. So the derivative of sine gives you positive cosine, and derivative of cosine will give you negative sine. And that has to do with that limit definition that we talked about. So let's look at a couple examples when it comes to trig. So if I have y equals 4 cosine of x, to get y prime, okay, that coefficients stays a coefficient. We kind of just bring them down. They follow the process. We multiply them when we need to. We leave them when we need to. And with cosine and sine, we're not really going to ever have to deal with the coefficient, so we just kind of want to bring them down. So we talked about how the derivative of cosine gives us negative sine. So that negative is not attached to the sine. It's actually attached to the coefficient of sine, which is a 1 there. So in reality, we have negative 4 sine of x. And there's our answer. We're done. On this side, we get y prime. Of course, the derivative of x squared gives us 2x. This is that sum and difference rule. We can just deal with them independently. And then, of course, plus negative sine of x. If I wanted to rewrite this, of course, I'd get 2x minus sine of x. Okay, so that kind of wraps up this video. What we'll do in class at the beginning of class is I'll prove to you the derivative of sine and cosine. It takes a little hinting. It's a little bit hard to do this on the video, so we'll do that first thing in class tomorrow. If you have any questions, come in and see me.